Hi everyone, this is Unit 8, which is enolate chemistry, and in this video I want to describe the synthesis of a sunscreen ingredient that my students are making in lab. Specifically, I'm going to go over the mechanism of a crossed aldol condensation. Okay, crossed aldol condensation. Why the word crossed? Crossed because you are reacting two different carbonyl groups, or two different carbonyl compounds. Now we're doing an aldol reaction, and to have a very successful crossed aldol, one of the starting materials shouldn't have a alpha hydrogen. You notice that this one has no alpha hydrogens. Therefore, that molecule cannot form the enolate. In the mechanism, we're going to realize that this will be the enolate, and because there's no alpha hydrogens here, this is not the enolate, and it's the molecule that's going to be attacked. I like to put a dot on the carbon that's being attacked just to keep track of all the atoms, and I could use that as a reference point. Okay. The product is a sunscreen ingredient. Let me give you a couple pieces of information about that. It's called dibenzyl acetone. It's a good sunscreen ingredient because it absorbs UV light. And the students in lab who are making this will see under UV light that it absorbs very, very well via TLC. The other thing you want to realize about this experiment, if you're making a stoichiometry table, is that it requires two molecules of, this is benzaldehyde, to react with one molecule of acetone. Benzaldehyde is the oil or the flavoring of almonds. And at the beginning of lab, you can smell the benzaldehyde, but at the end of lab, hopefully after purification, you do not smell any benzaldehyde, any almond smell. I think we're ready for the mechanism. Aldols and other type of enolate reactions are driven by the fact that you can deprotonate an alpha carbon. The alpha carbon, which is the carbon next to a carbonyl group. And that's what we're going to do first, and we do have base right there. Okay. When you abstract a hydrogen off of a carbon, you have to draw all the hydrogens off of that carbon. You just can't put the one hydrogen like this because you would be explicitly saying that that carbon only has one hydrogen attached. You should draw all three, and I require my student to draw all three. We're going to use base, OH minus, and we are going to deprotonate the alpha position, right, the alpha carbon. Base grabs a proton. Now, sometimes the professor will allow you to put the two electrons onto the carbon to make a carbon anion, but actually what happens is the oxygen anion is the preferred resonance, and we get this single bond up here to the oxygen, negatively charged, and we have that. That's an enolate. Okay, it's the oxygen anion form of the enolate. We also produce water, and I do like to put every product at each step that it was made in. And then we have the attack, right? The enolate attacks the carbonyl carbon. You got to draw the benzaldehyde. Since the benzaldehyde was not made in the previous step, you should introduce it over the arrow. Here's my dot. Okay, how do we get this connection? We get this connection by remaking the double bond of the carbonyl group, and then that forces this pi bond to attack. Opposite attract, electron-rich pi bond, electron-poor carbon, and we do form the tetrahedral intermediate. Now, am I going to run out of space? Let's see. I have this acetone. That carbon attacked the dot. So that's why I put the dot, so I can recite what else is connected to that dot. Well, now we have an O minus. We have the benzene ring, and we have a hydrogen. You don't have to draw the hydrogen. I'll draw it. Okay, just to emphasize that it's a tetrahedral intermediate. Now, what do we do? Let's protonate this oxygen and make it neutral. Let me go down this way. And how do we protonate it? Let's use water. Okay, we're under basic conditions, so it wouldn't. It makes a lot of sense to actually reform the base this way, like that. And now we have the neutral molecule. What is this molecule actually? You all know this by the term beta hydroxy ketone. Right? Here's your alpha carbon, and here's your beta. So this is typically the product of an aldol reaction is the beta hydroxy ketone or aldehyde. We have a ketone, alpha beta, beta hydroxy ketone. We're halfway there. Not quite halfway there, but we got one of the rings, one of the benzene rings onto the acetone. This is condensation. Condensation meaning you are creating a small molecule and it's condensing the small molecule. Typically it's going to be water, but sometimes it could be HCl or another hydrogen halide. But we are going to condense water, and we can't protonate this to make it a good leaving group because we're not in acidic media. It's still perfectly fine though to go ahead and strip off this hydrogen using base and kick out OH minus. We are in the sea of OH minus. So here's another OH minus hydroxide from sodium hydroxide. It's pretty concentrated, so it doesn't surprise me that we can go ahead and do the condensation. Or you can think of it as a dehydration, right? You're removing H and OH. This bond collapses to make a double bond, and then this one leaves. Okay. Now we are halfway home, because now we have this double bond between the two carbons. We have this benzene ring. It's conjugated. All the double bonds are conjugated, meaning that they can share their pi electrons because every single atom along this pathway is sp2. And sp2 has a p orbital. Those p orbitals overlap to allow the pi electrons to go to any one of these carbons, any one of these atoms actually, because oxygen is also sp2 hybridized. We did create water, and heck, we created one water molecule, H2O, and we created an OH minus, which is great because we don't have to redraw the OH because we're going to remove now the beta hydrogen, did I say beta? The alpha hydrogen on the other side. Okay, so now this is just practice now. Practice doing this over again on the other side. I like to make the oxygen anion. Your professor may allow you to make the carbon anion. Okay, it just depends on their preference. And I'm going to flip the molecule. So the benzene ring is now on the left. I have that. What else do I have? I have this O minus. And now I have the double bond here. If you're trying to keep track, this is the alpha carbon I'm removing the hydrogen from. Now this is your alpha carbon, same carbon. I just flipped the molecule, and I created water again. Same thing, okay? Just keep going. If you want to pause the video and see if you can do the rest on your own, that'd be great. Here's my dot. Remember how we attacked? We reformed the double bond of the carbonyl group, pi bond, up, and then we have this. Okay, it's a little bit tedious. You know what we could have called this actually? We could have called this a double crossed aldol condensation because we're doing a cross aldol condensation on each side of acetone. Okay, almost there, I think. Remember what happens here? We have to now neutralize or make that O minus an OH by protonating it. Let's use water. We didn't make water in the previous step, so we're going to bring it with the arrow. You see the idea here? If a ingredient in a step of the mechanism is not produced previously, in the previous step actually, in the preceding step, then you introduce it with the arrow. The other thing that I normally mention that I forgot to mention is that you should draw your green mechanism arrows from a source of electrons. And if you look, let me just finish this up. If you look at every single green arrow, I'm thinking that every single green arrow started from a source of electrons, whether it be a lone pair or a bond. Even the ones with charges, see, I still drew it from the lone pair. I didn't draw it from the charge. That arrow right here is coming from the lone pair, okay? Not from the negative charge. The negative charge is just a consequence, right, of the atom having a formal charge. Anywho, we created OH minus, so you have it as a plus OH minus, and then the arrow. You see the difference between having the reagent here and having the reagent over the arrow? It's because we made OH minus that I could have it here, not over the arrow. And I believe we are about done. Just have to do the dehydration. It's a condensation, but it's a special type of condensation because you're producing water, you're doing a dehydration. So I actually, while scanning my mechanism, I found one really tiny mistake, and maybe you at home see it too. Let me just finish this. H2O plus OH minus. You don't have to draw a lone pair, or you don't have to draw the lone pairs if you're not using them with the green arrow. And the mistake, it's kind of very minor, but let me zoom out just a tad so you can see the whole mechanism. The mistake I'm thinking is here I created OH minus, so I shouldn't have this under the arrow because it was made in the previous step. Looking for my whiteout, which I always have, but I don't right now. Oh, that's disappointing. So the arrow, oh, here it is. Obviously, I want to take off points for this, but I would put the arrow right there. Are we good now? I think we're good. Double check everything. Okay, you understand mechanism arrows start from a source of electrons, and for each step, you draw all the products of that specific step. Okay, great. How many steps is this? 1, 2, 3, 4, 5, 6, 7, 8. So I'm just counting the reaction arrows. So there are 8 of them. But where's the aldol product? 1, 2, 3 steps to the aldol, a 4th step to the condensation. So last thing I want to say, this is considered the aldol product, and this is the aldol condensation product. Now, you might have been taught that to push the aldol to dehydrate, to go from the aldol product to the aldol condensation, you want to add heat. Actually, in this reaction, we don't need heat because the driving force to lose this OH to make a double bond is so large because we get a very stable conjugated product. So the driving force is to make this double bond because it's conjugated between the carbonyl and the benzene ring. You do not need heat in this particular case. Okay, that is the synthesis of dibenzyl aldehyde. Did I say about aldehyde? Dibenzyl acetone.